Tamer, I work at SideFX, and welcome to my presentation on how to build a solver in Copernicus. So firstly, a bit about me. As mentioned, I work at SideFX. I'm an image processing TD, and I'm on the Copernicus team. I was previously an intern, and I joined the Copernicus team last November. These are some of the things that I worked on for Houdini 21. This ranged from making the entire node to just making like upgrades or additions. Some notable ones are the Baker, the Reaction-Diffusion Solver, or like the scattering tools for procedural texturing. If you've used any of these, you're automatically cool. And if you have any thoughts on them, please come speak to me about them. I love talking about them. So firstly, what we're going to talk about today is we're going to take a look at what solvers are and how they work in Copernicus. Then we'll lead into taking a look at the new solvers released for Copernicus in Houdini 21. We'll do a basic experiment with a block, and then we'll step it up a notch and write some OpenCL. I think I'm the first person to write code in these presentations, so hold on to your seats. If you're familiar with Vex whatsoever, I found it easy to jump over to, and I also made an effort to keep it somewhat simple, so you should be all right. Maybe this will scare you off completely and terrify you, but come speak to me and I'll try and convince you otherwise. And finally, we'll use it to recreate the Reaction-Diffusion Solver. Just quickly before we properly dive in, some disclaimers. There is somewhat bright stuff and somewhat flashy stuff. It's pretty tame, but just to make you aware. I also heavily customized my Houdini look. All the flags are different colors, and some of the layer of different colors is not a Houdini new UI. And also, I'll say solver simulation interchangeably, probably. So, yeah. So first, let's cover the basics. So I'm sure a lot of you already know what Copernicus and solvers are, but let's just get a baseline level of understanding. So what is a solver? Basically, solvers are special nodes which calculate things across frames, which means that they're time-dependent nodes. In the case of most of these examples here on the right, it works by modifying the previous frame's geometry, which creates simulation-like effects. And in Copernicus, we work with images, so we're doing an operation on the image every frame, and they're also mostly green. What is Copernicus? It's a 2D and 3D GPU image processing framework. It's a horizontal node graph like Apex and VOPs. And it's for making textures and doing compositing in one package. But as of Houdini 21, it is mostly texture synthesis. And it's meant for real-time image manipulation in 2D and 3D space. Just briefly as well, cables are a layer type in Copernicus, which allow you to store multiple layers in one wire, basically a struct of some type. So that means that here we're packing up multiple images into one wire, then we're doing an operation on that wire, HSV adjust, I think, which means that we're doing the operation on all 4 layers at once, and then we can then unpack them and do whatever we want with them. So as you can imagine, they're very useful in the network, but we'll get more into them later. So solvers in Copernicus, we added 3 for this release, and they're all super unique compared to each other. But because of the nature of the way solvers are made in Copernicus, they're all sort of formatted super similarly, so it's easy to talk about them in a general way. So let's go through them. Firstly is Pyro. This is not to be confused with the Pyro solvers in SOPs and DOPs. It's a 3D solver which runs over BDBs. Next up is Flow, which is a pure 2D fluid simulation, which runs over regular Copernicus layers, so that means like RGB or mono layers. And you can make cool-looking fluid simulations, and it's generally intended as an artistic tool to create advection effects for things like motion graphics. Last up is Reaction-Diffusion, which is what I worked on. It's a 2D-based chemical reaction solver, which simulates 2 chemicals reacting, merging, and diffusing. And again, it runs over regular Copernicus layers. Just because I think it's so cool, not at all because I worked on it, here's some nice examples of some of the animated and static patterns that you can create with this solver. I think that the beauty of it is that with literally 0.1 value of a parameter change, you can create an entirely unique pattern. Just briefly, some of the video examples I showed had 3D videos while telling you that 2D. In the example of Flow here, it is a 2D flow simulation, but it's been taken outside of Copernicus and used to drive a grain simulation. So while the base solvers for Reaction, Diffusion, and Flow are 2D, there's absolutely nothing stopping you from taking these elsewhere in other dimensions or areas of Houdini. So how do you even start with a solver in Copernicus? Well, you need an idea. Not really. Given how fast Copernicus is, you really can go into building these sorts of things by just playing and experimenting. You don't have to have a super rigid idea to start out. But what do you actually need to make a solver in COFS? So we need a block. So what is a block? They come in many different forms. In SOPs, we can create compiled blocks where we can compile node operations and then invoke them later in different areas. Or we can use them more commonly in things like for each loops. Blocks in Copernicus got a major upgrade in Houdini 21. Before, they could only handle a few types of layers and could only be used to compile. Now in 21, we have simulation, caching, live simulation, way more layer types, and they're also orange. It's important to note that for most of Houdini, blocks are not how you do simulation. You don't make a solver out of a for each loop and stops. But in Copernicus, this is how we do things. So I just wanted to point out the difference that blocks do very different things depending on which context they're in. So now that hopefully we understand the basis of what a solver, Copernicus, and blocks are, let's take a look individually at one of the solvers and figure out how it works in the network. So this is the flow solver in Houdini 21. We have the block begin and block end, and then a bunch of inputs and outputs. First, let's look at the main layers. That's not an official name, that's just what I'm calling it. These are what carry our primary simulation data, which feeds back per iteration. So what is feedbacking? Originally, we have the flow solver, and we input an image of this butterfly. Then inside the block, in the first iteration of frame, we distort the image, and then pass it to the block end. This image will then do a complete round trip and loop back to the begin block, where it will then become the input for our second iteration or frame. This is what this looks like in actual effect. On the left, we have a distort running once, and then on the right, we have a distort that's running within a block and feeding back on itself. So that's our main layers. It's important to note that for something to feed back, it needs to exist on both the block begin and block end. Now at the beginning and end, we have feedback and pass-through inputs, which in this example are cables. They allow for additional carrying of simulation data and data injection. So what does that mean? First, let's cover pass-through. So again, let's go with the example of trying to distort something. So we have this distort cop, which has some nice layer inputs for direction and scale. And we want to create a nice pattern and input these into those and create a complex look. So we create this huge network of complicated masking and noises and all the works. But there's a critical issue here, and you may be able to notice it by how ugly the green container looks, which is that everything inside a block cooks every iteration. So this huge entire network is going to slow down our simulation. It's not animated at all, it's just static masks. So this isn't great, obviously. So what we can do to bypass this is to pack up our direction and scale into a cable and create a cable input on the block called pass-through, which already exists in this case. You can call it whatever you want, but pass-through is the standard for COP solvers. Then inside the block, we can just unpack the layers and feed that into our distort node. Therefore, the huge network that we saw will only cook once at the very beginning, but we can still use the layers within the simulation, and it will run a lot faster. And next is feedback. The wording may be a little bit confusing here. This isn't had to do with how layers feedback if they exist on both block begin and block end. It's just another layer that exists on COP solvers. So what is it? With feedback, it's a little different. Basically, it allows us to carry additional data through the solver, which isn't a dedicated input-output that holds our traditional simulation data. So say we want to distort this image by using the scale input of an image which is simulating itself. So what we can do is add a cable input, which again exists in this case, called feedback, and we can input a noise pattern, let's say. Then we can distort that noise pattern, and then that will feed back itself. And then we can use that feeding back animated noise to drive the scale on our main distort. So it basically allows us to have extra data layers without having a separate block. So that's feedback. It's important to note that these are not mandatory for your simulation solvers whatsoever, just in case I gave that impression. They're just quite useful to have, and again, are the standard for COP solvers. So let's build a simple simulation. So I'm just going to get a few nodes added to get started, so like a SDF shape with a star, and then I'm going to set up some inputs on the block, so distort and star. So the distort is going to be the layer which will feed back, and then star is our static shape. Then in the block, I'll create an add node, which adds the star pattern onto the distort layer, making sure that distort also exists on the block end as well, so that it will feed back. Then I'm also going to add in a bright, and put in 0.9, so we darken the result. So what we should see is that each frame, the star shape gets added onto the distort layer, and all the previous stars gets darker, which should create some sort of trail effect. So if I display the block end and drag around the star, creates a trail. I can also make it more complex, so I can add a distort by slope and plug in a fractal noise, and then I can also animate it because that's more fun. And then once I play the simulation, you should see that it becomes all distorted and creates a weird, interesting look. So let's get into the main meat of this presentation, which is building the Reaction-Diffusion Solver and writing OpenCL. So this presentation isn't about how reaction diffusion works on a super, super deep level, but I'll touch on it a fair amount. So reaction diffusion is a process where two interacting chemicals spread out or diffuse across a medium, with one of the chemicals reacting and converting to the second chemical, while they both spread out at different rates. Meanwhile, chemical A is injected into the process, which is called feed, and chemical B is removed from the process, which is called kill. So that's actually a gross misrepresentation of reaction diffusion. That's just reaction diffusion in one model or implementation, which is the Gray-Scott model. This is arguably the most famous model, and when you search up reaction diffusion in Houdini terms or even outside Houdini, this is 90% of the time the model that you'll see. The Gray-Scott model is just a way of describing how the two chemicals react to each other, as well as the environment that they're in. There are many other ways of describing reaction diffusion, even of upwards of like 11 chemicals, but those are pretty complicated. So these are the Gray-Scott equations. They may look pretty scary right now. Even I hate looking at this, but trust me, it's way simpler than you think. And once you see the implementation, hopefully it should become easier to understand. So let's break it down somewhat. Firstly, we have our changing chemicals each frame, so just the chemical values. Then we have what's called our Laplacian function, where we basically check on all of our neighbor chemical values and compare the difference. Then, because we want A to diffuse faster than B, we just multiply this by numbers, so diffusion coefficients. And then we can add in our reaction rate, which is the probability that A and B will merge. And then for A, we add in our feed rate, and for B, we subtract our kill rate. Pretty simple. So reaction diffusion has certain characteristics about it, which make it difficult to manage and somewhat challenging to art direct. So as sort of a caveat to those looking to make this sort of thing, some of the things that you might run into are, for example, that it requires a lot of iterations. Working at the pixel level, so as you can imagine with a large image, things need to go a lot faster. It can be resolution sensitive, it depends on the implementation, but I had to do some work to fix this. It exhibits non-linear behavior, meaning that just because you drag a slider smoothly doesn't mean that it will go smoothly within the reaction. And because of that, it struggles with fast input changes as well. And it's also sensitive to initial conditions. This isn't to turn you away from reaction diffusion, just more to make you aware of the challenges. I had to struggle a lot with these during their development. I think I did an okay job of making the solver be more stable, but some of them are just intrinsic to how reaction diffusion is. I won't get too deep into how I solve some of these, because it gets very technical at that point, but if you want to check it out, you can download Houdini and look inside. So I want to break down how we can translate reaction diffusion to a Houdini solver so we can get a bit of a plan. So we have two chemicals, A and B, which translates into it running over a UV layer of float 2. So this is a UV layer that can store chemical values. Then we have the reaction equation where A is killed and B is fed, which can be done through simple parameters or layers. Our chemicals diffuse through the medium, which can be done through the Laplacian function that I mentioned. A diffuses faster than B, which again should be done through diffusion parameters or layers. And then finally, reaction seeding. So the way to actually start the reaction in the Gray-Scott model is to have a disturbance in chemical B. So we can do some sort of work to create an initialization mask. So let's start setting up the solver. We need a block, obviously, the first step. Then we can add our chemical UV layer to handle our chemical values. Then add in our kill and feed, and our diffusion coefficients as layer inputs. This isn't entirely needed. As said, I could do parameters, but it's nice to be able to vary the values across the image, which we can do with a layer. So now I'm going to put down the scariest node in all of Copernicus, which is the OpenCL carp. It's actually not that scary. As mentioned at the beginning, if you're familiar at all with Vex, it shouldn't be too difficult to jump over to now that OpenCL has become more user-friendly as of Houdini 20. So what does it actually do? It's essentially a node where we can code behavior. We can first bind the layers or parameters which we want to use in the code. Then we can do stuff with the values on the layers, and then set the values that we changed back onto the layers. So first we want to bind all of our kill, feed, chemical, and diffusion coefficients. So I'm going to start binding that. So we bind a chemical diffusion, which isn't the diffusion coefficients, but I'll get into that later. We can also bind our kill, feed, and diffusion coefficients. You also might notice various symbols next to the names here, which are flags. So in binding, we firstly bind the type, so an image layer or a parameter. We set the name, which can be anything, and then we can set various flags such as the read-write behavior or its type. So in some examples, we have a monolayer called chemical, which is optional as it uses a question mark, which means that we don't have to have it as an input for the code to run. Then we have an RGBA layer, which has the write flag, which is an and sign. This means that it's a layer which can get, which is read, but also can be written to. Then we have an RGB layer, which is using exclamation mark, which is not readable. you'll see it turns up as white instead of the usual RGB color, which is because it's not really meant to be used this way. Instead, it's meant to be used in combination with the right flag to signify a layer which isn't read but is written to, so only being outputted. So now we have the binding done, we can move over to writing some code. Hold on to your seats. So now we have the layers binded, and in our kernel, we can write what our cop does. So we're first going to build the laplation function, which is the very important neighbor checking stuff. So first thing I'm going to do is initialize a couple of variables, so diffusion, which I'm going to set to 0, and chemical, which I'm going to set to the chemical layer, which means that when this runs, the chemical variable there will become the current value in the chemical layer at whichever pixel we're working on, essentially. Now we can make a for loop, so we're going to check on the vertical axis everything above or below us by one buffer index, and then inside that we're going to do it on the x-axis, which means combined we're going to do all of our neighbors, and then we're going to exclude ourselves for reasons I'll say in a second. Then I'm going to set up this multiplier variable here using a global binding called @dpdxy, which is the space between pixels, and I'm going to multiply it by some magical number. Then I'm going to use it to set up this weight variable. So the math for this little bit here, I do not have time to go into today, but essentially what it does is make our reaction resolution independent. So because at high resolutions, the space between pixels shrinks, and this basically balances that out. So now we can write our actual function. So we want to output the current diffusion value to be equivalent to itself, plus the difference between the current value of our chemical and whichever buffer we're sampling around it, also multiplied by our weight function for resolution independence. This is why we excluded ourselves, because there's no point adding ourselves and then subtracting ourselves. So just wasted performance, basically. And then we can set that to our diffusion layer. So that's the first step. So what does this actually look like? If we look at this really low resolution example, we are going over the image and checking on our neighbors and comparing the certain values to whichever one we're processing. It's kind of hard to see in this small resolution example. So if I upscale it a bit, you can see that it sort of creates an outline effect. This is what it looks like on the actual reaction diffusion. Here on the left, you can see the pattern, and on the right, what the diffusion function produces. So the green channel is the B chemicals diffusion, and the red channel is the A chemicals diffusion. So now we have the diffusion in reaction diffusion. But now I need to write the reaction part. So what I need to do is go back to the options of our OpenCL cop and enable the rightback kernel. Then underneath our main kernel, we can write @rightback. So our rightback is where we're going to write our actual reaction equations. We just needed the main kernel to set up our neighbor function. So the rightback is essentially another kernel which runs directly after the first one within the same cop. So it's like having two kernels in one, basically. Just to be clear for this presentation, I'm not going to show all of the features of the main reaction-diffusion solver because I don't have time, such as the boundary limiting, safe scaling logic, or the kill feed non-linear remapping. But again, you can go download it and look. So first I'm going to copy my kill and feed layers to a couple variables, then create some other variables which we'll use to track the change in chemicals A and B. Then I'm going to sample our current chemical, then split that up so it makes it nicer, easier. Then I'm going to sample the @diffusion. So this isn't sampling the diffusion in the block because there isn't one. This is actually sampling the output of the first kernel and basically passing it directly to the rightback kernel. Then I'll add in our reaction rate. And then finally, we get our diffusion coefficients. So now we can write our actual reaction equation. So we have delta A and delta B, which is the change in chemical, as well as our laplation function multiplied by the diffusion coefficients. So we have this part done. Then we can just add or subtract our reaction rate, and then implement our kill and feed. Then we just need to take the current A and B from our current chemical value and add our delta change multiplied by the time increment. And then we can clamp it and set it, and that's it. That's reaction diffusion. That's the reaction part. So now we can go back to the network, and we can't hit play just yet. First, we need to set up the layer inputs because we have nothing right now, so it won't work. So I'll just add in a constant for kill, which is a value of 0.06, and feed a value of 0.037. Then the diffusion coefficients. So as mentioned a couple times, A diffuses twice as fast as B. So the first constant is set to 1, and the second is set to 0.5. And then I need to do the initialization mask. So as mentioned, the way to actually start the reaction is to have a disturbance in B. So for the red channel for A, I just set it to be 1 all around. And for B, I just mask a star shape with some random noise. And then that's it. I press play, and there you go. There's reaction diffusion. We can see it simulating in the network. And it might be notable to say that I'm actually remapping this and making it black and white because the real chemical values aren't very visually friendly, which you can see here. So because we're in a block, we can do all sorts of chaos, such as distortion. I think I like distortion a lot. I've used it as an example a lot. And I can add a distort by slope and plug in a fractal noise. And as you can see, when I play this simulation, the reaction gets distorted and curly in all sorts of interesting ways. It's very fun to play around with. So now I actually want to use this in something. So I'm going to break down one of the shots that I did for the Houdini 21 launch. Just to clarify, the original hit file was made by an artist on the Houdini 21 alpha named Martin Winkler. But he gave us permission to use it and modify it and such, which I did. So just for ease of talking, I'll be speaking in I instead of he did this or whatever. So first, I just combined some SDF shapes to make 3 dots, which we'll use as our activation mask. So this is where the reaction will grow from. It's important to note that in the final Reaction-Diffusion Solver, it takes care of this reaction seeding stuff for you. So all you need to do is just input a mask, basically. Then I'll plug in some noise into the scale to get some variation. And that was it. That was all that was to it. It's very simple, but it creates a nice complex effect. It goes from the 3 places that we chose, and it has a large variation in scale. But then I wanted to take it outside of Copernicus. So in a SOP solver, I just took a grid, and I applied the Copernicus map to drive the position multiplied by the value of the pixel along the normal. So as you can see, that makes the geometry go up with our reaction. And the longer pixels have been stable or white for, the higher up it is. This is a cool effect, but it wasn't exactly what I was looking for. So what I did was remesh it. So this recalculates the normals for us every frame, which means as the mesh goes up, its normals get recalculated, causing it to bubble out. So to visualize that, this is what the mesh first looks like when we push it upwards along the normals. Then we remesh it, which recalculates the normals for us, and it also smooths things out a tiny bit. And that creates this spherical bubbly effect. And this is the result. You get this very weird looking effect. It looks like mold growth. It's very, very simple, but it looks cool. And then here's the final shot, which was run through Solaris and Karma XPU. So here's some more fun that I did with it. You can do a bunch of stuff with this solver. You can run your cats through it. That's always fun. Fun fact, doing this was actually how I discovered a memory leak early in the dev cycle. So that's always fun to do. So what are the takeaways? Firstly is how you build a solver in COPS. You use the block, and you use layers on both the begin and end block to make them feedback. Oh, sorry, I didn't hit play yet. Cables, they're useful in many ways. They can organize your node network, allow you to do repeat operations on many layers at once, and can optimize your simulations as we saw. Thirdly, which hopefully is not a lie for some of you, which is that OpenCL is not that scary. Maybe for some of you, the example was getting pretty complex, but all of the COP nodes are written in OpenCL, so it's an extremely powerful tool to know if you're messing around with COPs, even to do simple things. And finally is that reaction diffusion can be used to make organic growth patterns. Here's some of the people that helped me out along the way: Omar, Fiona, Nicola, Jeff, Jessica, Scott, all of the SideFX interns. I will definitely miss them, and Martin Winkler. And that's it. Thanks for listening.
All right, last chance for questions.
Oh, God.
Nice work.
Hi, Jeff.
Hey. So I saw this was all in 2D. Have you done any tests with 3D with the reaction diffusion?
No, because generally, like, you need to have... there's the Pyro 3D, which runs over VDBs, right? So this would have to be converted to run over VDBs to run in 3D, which, I mean, you can do yourself if you're, brave enough, but eventually, maybe it will become a thing. So, yeah.
Cool. Nice work.
Thanks.
Hey, Alex. Curious about UV scenes. I'm guessing if you have like a character, I'm thinking with a UV that's unwrapped, it's not going to be able to traverse. It's not going to be able to know that there's like a seam, right?
Yeah.
So you'd have to have like a like an alternate UV or something. Okay.
Yeah. So there is a way around that, and it's called this thing called adjacency rasterization, and it basically allows you to teleport pixels. You basically find where the UV boundaries are across different areas of the map, and it basically smoothly teleports them across. It doesn't exist yet. There is like custom-made community implementations made in Vex, but it doesn't exist yet because if we were to do something like that, we'd want to do it in GPU-based. So it does exist online. So yeah, it is possible, but not in native Houdini yet. So yeah,
Cool.
maybe I've said too much. Oh well.
Any other questions?
I'll be around the entire week, so if you just want to come chat, then
Thank you for the great presentation.
cool. Thank you.